Assalamu alaikum. In our last lecture, we explored the basics of hash tables, how they store data, how hash functions map keys to indices, and how lookups can be incredibly fast. But we also hinted at a challenge, collisions. Today, we'll take a closer look at what collisions are, why they happen, and how we can deal with them using different resolution strategies. Now, consider the case of a fruit shop. We want to digitize it. We have a hash table with 10 slots, indices 0 to 9. First, we hash and insert apple, right? Lands at index 5. Next, we take guava. Now, its hash points to index 3. Then pear. It goes to index 2. So far, so good. Each fruit has its own slot. Now, we want to insert papaya. Now, when we hash papaya's key, it also maps to index 2. But index 2 is already taken by pear. We have just encountered a collision. Two different keys mapping to the same slot. So what is a collision? A collision happens when two different keys hash to the same table index. This can happen because of limited table size. There are only so many slots. Or hash function overlap. Different keys which can produce the same hash value. Since collisions are inevitable, we need strategies to handle them. The two most common strategies are open addressing, where we store all elements directly in the table. If the target slot is full, we use a probing sequence to find the next available slot, or chaining. Now, each slot holds a linked list of all elements that hash there. Multiple items can share the same index in a list. Let's start with linear probing, an open addressing method. We go back to our fruit shop, right? So papaya's hash results in index 2, but pear is already there. Here's what we can do. Check the next slot, index 3, but guava is there. So we move to the next slot, which is index 4. Now this one is empty. So we simply insert papaya at index 4. Now linear probing works by checking consecutive slots until we find a free one. The advantages of this is it is very easy to implement. It has a good use of cache memory since elements are stored close together. The cons are it can cause primary clustering, which means large groups of occupied slots form, which slows down insertion and searches. So one of the key points to remember here is when you reach the end of the table, you wrap around to index 0 and continue searching from there. Instead of linear probing, we could also use double hashing, which is also a kind of an open addressing technique. Here's how it works. First, we use a primary hash function to get the initial index. Then use a secondary hash function to determine the step size for probing. Now the rule here is the step size must be a coprime with the table size m, so that all slots can be visited before repeating. Example includes the same papaya, right, which has to index 2. When we apply secondary hash to it, right, so h2 with the value of k, we use the formula 5 minus k mod 5. Now this, in the case of papaya, would give us a step size of 3. Now, because m, which is 10, and 3 is a coprime, so we are good to go. Now we probe. Start at index 2, which is already taken. So next, apply the step size, 3, go to 5. If it is already taken, then go to index 8, then index 1, then index 4, then index 7, until we find an empty slot. If the step size and table size are not coprime, we could end up cycling through the same few slots and never reach others. Now, let's look at chaining. Instead of finding another empty slot, each index holds a linked list of entries that share the same hash value. So if both pear and papaya hash to index 2, we keep them in the same linked list. Chaining avoids the clustering problem seen in open addressing, and it allows the table to store more elements than it has slots. But it requires extra memory for the linked lists, and lookup times can grow if the lists get long. The load factor measures how full the table is. It uses the formula shown over here, which is alpha is equal to number of stored items divided by the size of the table, m. Now, if alpha is low, this means there would be fewer collisions and faster performance. If there's a high alpha, this means there will be more collisions and slower performance. So from our fruit shop, if m is 10 and we have 7 items, alpha would be 0.7. Performance is good. However, if m is 10 and we have stored 9 items, then alpha becomes 0.9. Collisions will become much more frequent. So in order to resolve this, we can simply set a threshold, let's say 0.75. When alpha becomes 0.75 or a bit higher than that, we simply rehash. Or we resize the table first, often doubling in size, and then rehash all the elements which are inside the table. So a good hash function, again, we covered this last time as well. A good hash function should distribute keys uniformly, so to avoid clustering. It should be fast to compute, and it should produce minimal collisions for the expected data set. So the methodology that we used in our example was a very poor example, right? So when the hash function is k mod 10, as in our fruit shop, many keys end up in the slot 2. However, a better approach could be either use a prime table size, let's say 11, or combine multiplication and modulo methods. If we have strings, let's say fruit names, we could use polynomial rolling hash for better spread as well. Collision resolution isn't just academic, it's everywhere. Your databases use it for indexing tables for lightning fast lookups. Your compilers use it for storing variable names in symbol tables. Web browsers to cache DNS lookups. And in cybersecurity, it is used for storing hash passwords with salt for security. Finally, in e-commerce, your shopping carts are often mapped to customer sessions using hash tables as well, and they require collision avoidance. To sum up, collisions are unavoidable in hash tables. Now, open addressing uses probing sequences to find empty slots. Chaining stores multiple items at the same index using linked list. So what we want to do is we want to keep the load factor low. We want to choose a good function and rehash only when necessary. Mastering collision resolution ensures your hash table stay fast, efficient, and reliable. Thank you, and keep practicing.